All right, welcome back to our fifth module of the anomaly detection workshop. In the last three modules, we talked about methods on spatial data, meaning that we assumed that at least the nominal data came from a fixed distribution. Potentially even the anomalies came from a fixed distribution. Now we're going to leave this setting and talk about another very important scenario, namely time series. So what are time series? At first glance, the data that we get from a time series is not very different compared to spatial data. The only difference really is that it's indexed by time. So here we see a typical example of a time series. It depicts the monthly beer production in Austria. So we can see here the behavior over time. So here you can see this cyclic behavior, and also that over a longer range, the beer production even increased significantly over time. Okay, why is anomaly detection on time series different? I think the difference is best seen if we compare the typical task that we have on a time series with more classical tasks. For instance, let's have a look at a classical regression task and in the time series domain, more common task of forecasting. In a regression task, we have the independent parameters. In this case, this is only one-dimensional, the x that you see down below, and we have the dependent parameter, the y. We usually assume that x comes from a fixed distribution and that y is computed via some deterministic function f, plus potentially some measurement noise epsilon, which is usually modeled as homoscedastic and very often as a normal distribution. So since we assume that x comes from a fixed distribution, we can see that as we gather more and more data, we get a clearer and clearer view of the function in the support of the distribution. This is different if we want to do forecasting on time series, because now we have given a history of the process. That means that for time series, we can predict the future only to a very limited extent, and that uncertainty quantification is even more important in this case. Additionally, the data that we get from a time series is not drawn independently from some distribution, but we have non-trivial correlations between the points in time. So I hope that gave you an idea that we're really talking about a very different scenario. In the next lesson, we are going to talk about how this affects anomaly detection. As we've learned in the last lesson, time series are different from spatial data by the autocorrelations that we find between the points in time. So that means that we very often do not only want to identify individual points, which we think are anomalous, but we also want to identify whole patterns in the time series, which we find anomalous. So these are the most typical patterns of anomalies that we can find in time series: point anomalies, context anomalies and change points, and pattern anomalies. So let's see what those are. So first of all, point anomalies. These are the ones that we've also tried to identify when we were working with spatial or IID data. So these are points that do not fit to the rest of the time series. Okay, a bit more interesting are context anomalies. In this case, we talk about anomalies which are not necessarily anomalous if I look at properties of the time series as a whole. So for instance, not anomalous with respect to the global mean or the global variance, but they are anomalous in the context in which they appear. So in the example that you can see, we have the case that the time series at some point switches its behavior. So more precisely, the mean changes of this time series. So you see in this interval here, the mean is way higher than we have before that and after that. The point that we observe here in the middle of this red circle, it would be perfectly normal if it would have appeared like on the left side of this time series or at the right end of this time series, but right in the middle, this is rather unusual. So this is a context anomaly. Very related are change points in the time series. So in this example, we have two change points. These are exactly the points where the behavior of the time series changes. So we have this here on the left side when the mean raises up, and then on the right side when the mean goes down again. Typically, it depends on the downstream task whether you want to identify change points as anomalies or not. In certain scenarios, these change points are perfectly normal and expected over time. So in many cases, you would not count them as anomalies, but sometimes these are exactly the points that you're looking for. As a summary, change points mark regime shifts in the underlying data. And regime shifts are one example of where context anomalies can appear, but they can also appear in the context of seasonal patterns. Finally, we want to look at the notion of pattern anomalies. In this case, we really need to look at several points, and only the pattern that they build is anomalous. So the values that we see are not anomalous. I think this here is a rather good example. Here in this case, we see that the time series has a certain variance over time, but only in this case we suddenly get a flat line. Then all the individual points here, which are all at 0, I think, they are perfectly normal. They are perfectly in the mean of the time series. However, like observing the same value over a longer period of time is something that we can directly see to be very unusual in this time series. Next, we want to talk about how to model the behavior of a time series mathematically. We have already discussed that time series differ from IID data by the correlations that we find between time. Now we want to talk about how to model this mathematically. And this is where the concept of a stochastic process comes into play. So what does that mean? We model all points in time, all observations that we gather over time by individual variables that do not need to be identically distributed anymore. So now there are at least three important properties that we want to look at. First of all is the mean at time t, the variance of time t, and then the covariance between the variable at time t and the variable at time t prime. A very important concept on time series is the so-called stationarity, which tells us that these three quantities of interest are basically constant, meaning that we have a constant mean at every point in time t. We see that the variable xt has a mean mu. Also, the variance is supposed to be constant here, meaning that for all points in time t, we have that the variance xt is sigma squared for some fixed sigma. Finally, we want that the covariance is time invariant or translation invariant, meaning that the covariance only depends on the distance in time between 2 points. So for any t, we have that the covariance between xt and xt plus k is some value lambda k. So you probably wonder, okay, why do we want stationarity in a time series? I think this is best explained when we look at certain examples. Let's have a look at the time series which follows the following equation. So we have that the value at time t is equal to phi times the value at point t minus 1 plus some epsilon t, where we say that epsilon t is normally distributed, let's say again, a standard variable, and all these epsilon t are independent of each other. Now looking at this parameter phi here, we can see that the behavior of the time series can be very different depending on the value that we have here. If this parameter phi is larger than 1, then we have an explosive process, meaning that the growth of the time series or of the value is exponential, which is of course not stationary, but also rarely observed in practice. More interestingly is the case where phi is exactly 1, because then we arrive at the infamous random walk, which is also non-stationary. And finally, if we have phi smaller than 1, then we actually have a stationary process. So now let's look at the behavior of a stationary process and the random walk. So in the image on the right, you see in blue samples from the random walk. Our xt equals xt minus 1 plus epsilon. In green, you see samples from a stationary process. Here we have chosen phi to be 4/5. So, and I think you can directly see that these two time series behave very differently. While the random walk seems to be very erratically, we also seem not to be able to bound the variance. While in the beginning we have rather low variance, all the samples are kind of close to the initial value. Further away, the different samples can differ very, very distinctively in their order of magnitude. On the other hand, if we look at the green lines, then although we have started the time series at this arbitrary value of 25, we can see that all the samples from the stationary process behave very similarly. They very, very quickly revert back to the original mean, which is in this case 0, and then they kind of stay in that range forever. I hope this image already convinces you that compared to a stationary process, it's way harder to analyze a non-stationary process. So stationary would be something that we would really like in our time series. So let's summarize what we've seen in the image. So first of all, the stationary process was very well behaved and quickly reverted back to the mean of 0. The non-stationary process can move in very unpredictable ways. So the reason for that is that for a random walk, we just start off with the value that we assumed at the time step before, and then do some random movement. While in the stationary process, where this value of phi is smaller than 1, the effects that we've seen in the past wear off over time. We can also see that if we take a look at the conditional expectations. Namely, if we look at the random walk, then we can see once we observe the value fxt, the expectation of all the values in the future will move to this value xt. While for a stationary process, it is the case that the further we go away from the observed value, the closer we get to the original mean. So, teaser for you, can you explain why these two time series behave in this way? Okay, then let's try and see why this is the case. So let's first try and compute the expectation. Or let's first try and compute the conditional expectation for xt plus k. So in this case, we assume that we've observed xt. So now we can basically plug in the definition of this random walk. So we have, this is the expectation of xt plus k minus 1 plus epsilon t plus k, given xt. Now what we can do is basically repeat this process of plugging in the definition until we have xk in the expectation. So let's do that several times. And then we arrive at xt plus the sum of all these epsilon ti. So and now we can see why this is xt, because, well, the value of xt, given that we know what xt is just xt, and the expectation over the sum of these epsilon t is 0, because every individual variable had mean 0 of these epsilon ti. So that means that is indeed just xt. So okay, now let's try to understand why this is not the case for yt plus k. Right. So if we have a look at yt plus k, then again we can do the same substitutions and we will see that the effect of the yt will wear off. So first in the definition, the yt plus k minus 1 goes in with a factor of 4/5. So now I'm just going to do the substitution 2 times, but you can see that the factor quickly moves towards 0. That we get, because now we have again the 4/5, and now we get another factor of 4/5, and yt plus k minus 2 plus epsilon t k minus 1 is epsilon t plus k. And now you see that already epsilon t plus k minus 2 only appears with a factor of 4/5 squared. And this, of course, exponentially proceeds as we go back to yt, meaning that the effect of yt to xt plus k exponentially wears off as k gets larger. And this is the reason why we revert back to the original mean. So now we know why we prefer to work with stationary time series. However, probably if you have some experience with time series analysis, you already saw that more often than not, you will have to work in practice with non-stationary time series. That, of course, does not mean that you cannot do anything, because in many cases it is possible to transform the time series so that we get a stationary time series. For instance, if we look again at our random walk, then we can see that basically if we would just subtract the previous value from the current value in the time series, then we already get that the entire time series is just independently normally distributed, because all that's left is just the epsilon t. And so here we really see that all this erratic behavior that we saw in this random walk really just came from this deterministic part, basically naming that we always add the previous value to the epsilon t. And this is something that we can easily get rid of. So there's some notation that's useful to introduce here, namely the so-called lag operator, which we write as L of x, or sometimes we even leave out the parentheses and write it multiplicatively. And the lag of xt just gives us the previous value xt minus 1. So this allows us to rather conveniently write the equation that we have up here as epsilon t equals 1 minus lag of xt. This operation is also called differencing. Now we can have a look at the difference time series of our random walk, and it looks just like that. And I hope you see that this looks pretty much like a random noise process, which it also should be. So we should have IID samples from a standard normal distribution in this case. Again, this is something that you should keep in mind because, as I said, in practice you more often find non-stationary time series rather than stationary ones. There are two very typical phenomena that you can observe which lead to non-stationary time series, which are trans and seasonality. In the upcoming lesson we are going to talk about how to get rid of them. Alright, let's talk about how to handle trends and seasonalities. Let's first cover the trends. A trend in a time series is a tendency to move towards lower or higher values, which is observed consistently over a longer period of time. So down below we have an example of a time series. Here we depicted the sales of shampoo over a 3-year period. And I hope you can all see that this seems to be a rather successful company. I guess you can all already spot the trend that we have in this time series. Anyway, sometimes, especially if we have high variance, it can be hard to visually assess whether there is a trend or not in a time series. And there is a little trick that helps us to do this assessment visually. So we can apply a moving average to the time series. That means that we go through the time series with a sliding window and compute averages for each point in time. This gives us this slightly smoothed curve where you can see hopefully the trend much better than in the original time series. Of course, the question now is, how would you describe the trend in this time series? So think about this for a moment. And I guess then you all say that you see clearly a positive trend in this time series. And possibly you also already conjectured that this trend is not even linear. It seems to be higher order. I would guess quadratic in this case. So how do we get rid of trends in our time series? The answer is again the lag operator, which in this context is sometimes also noticed as this nabla, referring to that it's some kind of differencing of the time series. So this nabla is just the lag operator that we learned about, 1 minus lag of xt, so xt minus the previous value from xt. Or when it comes to removing trends in a time series, we very often do not want to apply this lag operator only once, but potentially several times. So the case order differencing operator nabla k is defined as 1 minus L to the k xt, which can be then computed with the binomial formula. How often do I need to apply this lag operator or the differencing operator? Well, in general, you can say if you have a linear trend in your time series, then applying the differencing once will remove this trend. And if you have a case order polynomial trend in your time series, then case order differencing will remove the trend for you. So now let's have a look at the shampoo sales again. So first of all, we did one differencing of the time series, and you see the result depicted here. So looking closely at this time series, I think you see that there is still some trend present, a positive trend still, but now it rather seems to be linear. So what can we do? We apply the differencing again, and now we see that there's really no trend present anymore, which is consistent with what we've talked about before. In the next lesson, we are going to talk about how to handle seasonalities. So now let's talk about seasonalities. First of all, what is a seasonality? A seasonality is the cyclic behavior that we observe over fixed periods of time. So very often the periods will be something like yearly periods, monthly periods, daily periods, and so on. A very good example is depicted down below here. So here we have the minimum daily temperature in Melbourne, Australia over several years. And I think you can easily spot this clear 12 months seasonality. So in this example of daily temperature, the seasonality is very obvious, and it's also pretty easy to spot the period of the seasonality because we basically know that it must be a yearly seasonality. Sometimes this is more challenging, and there are certain tools available to help you identifying seasonality. One of the most important here is the autocorrelation function, which describes the correlation between a variable and their lagged version. So here we need that the process itself is stationary, at least in mean and in variance. So the autocorrelation function only makes sense if we have a stationary time series. And here, if we have one with mean mu and variance sigma squared, then the autocorrelation can be computed by the following formula. So let's have a look at our daily temperature example. So here we computed the autocorrelation function for, well, roughly 2 years. And I think now you can pretty see the correlation pattern. It's as beautiful as you can get it in this example. A time series with a seasonality cannot be stationary because the mean is changing over time. So this is definitely something we want to get rid of. So how can we do that? Again, the lag operator is our friend, but we need to apply it in a slightly different way, because now we are going to use lag k differencing, which we denote with this lambda low k here. So which is defined as 1 minus L to the k times xt. So please note here the difference to case order differencing. In case order differencing, the power of k is outside of the parentheses. So here only the lag operator is raised to the case power, which means that we subtract the value xt minus k rather than just the previous one. So this is really something different than case order differencing. So now if we apply this to our daily temperature data set with a lag of exactly 1 year, then you can see that the resulting samples already look like white noise again. We can also here look at the histogram of the distribution of the values, which also looks approximately normally distributed. We can also have a look at the autocorrelation plot again. Here we see that we were able to essentially remove all autocorrelations within this data, so meaning that we're really talking about a white noise process again, which is then pretty simple to analyze. Now that we've learned about the basics of time series analysis, let's talk about how to do anomaly detection in time series. In this lesson, we are going to talk about a very common approach for anomaly detection in time series, namely anomaly detection by forecasting error. The idea is here, if we have a very good forecasting model, then it should be able to predict the upcoming values rather reliably. So now, if we observe a high forecasting error, it's pretty likely that the observation is really an anomaly. So if we want to talk about anomaly detection via forecasting, we of course need a forecasting model. And we are going to talk about a classical, nevertheless very powerful model, the so-called SARIMA model. SARIMA is a model which consists of several components. We write them down just below here. So it's the AR model, an MR model, integration and seasonal components which make up the SARIMA model. And now let's talk about these individual components. So first of all, the AR model stands for autoregressive model. In this case, we describe a process where the current value comes to be from a linear combination of the previous values plus again some independent noise. Now we can specify an autoregressive model again with the help of the lag operator. So the ARK model uses k lags. It can be written in the following form down below here. So this basically simply describes that the current value comes to be via this independent noise and a linear combination of the previous values. Maybe as a small side remark, so there is a characterization of when an autoregressive process is stationary. This is the case if the characteristic polynomial, which is the polynomial that we get if we just replace this lag operator now by a variable set. And if we interpret this over the complex numbers, and we see that all the roots of this polynomial lie outside the unit circle in the complex plane, then we know that we have a stationary model. So the next part of the SARIMA model is the MR part, which stands for moving average. So in this case, we are not going to build a linear combination of the previous values xt minus I, but a linear combination of the epsilon t minus I. So here again, we can now write xt as a linear combination of the current shock or the current epsilon t and the previous ones. Again, as a side remark, moving average models are always stationary. So maybe you can think for yourself, do you see why this is the case? If you don't see that directly, I give you a little hint. Keep in mind that the epsilon t are all IID distributed. I think then it should become rather easy to see that. At first glance, it might seem a little bit unintuitive to have the regression over the epsilon t rather than the xt, but maybe it makes sense to look at a small example where it can make sense to model things like that. So let's have a look at the hypothetical example of sales of earthquake survival kits. So in this case, you can imagine that every individual earthquake that you observed in the past is a reason for people to buy a survival kit, because they remember this earthquake, maybe they had damages or something like that. They think it's reasonable to buy a survival kit. But as time progresses, you start forgetting about the events that happen. And so the earthquake sales start to decline again. And this is, I think, a good example. So in this case, it's really that the individual shocks that we had in the past influence the number of sales that we had, rather than the accumulated values, which is what you would do if you choose an autoregressive model. So here we can have an example. let's say we have our earthquake strengths distributed something like that. And then let's say after a year, 90% of all the people still remember this earthquake. And every year, kind of 10% of the people that still remember this earthquake start forgetting it. Then you would see something like that. So here we have the earthquake curve, the strength of, let's say, the strongest earthquake per year, and how this behaves or how this influences the earthquake sales. So I think here you can pretty clearly see the effect of the moving average over the earthquakes. So now let's combine these two models, the autoregressive model and the moving average model. In this case, we basically just plug these two equations together. So on the left side, we have this linear combination on the xt, while on the right side we have this linear combination on the epsilon t. At first glance, it might seem hard to interpret what's going on here, but there is actually a very intuitive way of looking at this, because you can see the autoregressive model as making predictions over time. And of course, these predictions will not be 100% accurate. And the difference between what has been predicted and what is really observed are actually the epsilon t, if our process really behaves according to this model. So meaning that we can do prediction over time, step-by-step prediction, observe the errors, and then use this moving average part here in order to adjust our model according to the errors that we've observed in the past. So if we have consistently predicted like too low values in the past, then for the next prediction we can correct for that by adding this error to our next prediction. This is exactly the idea that we see in the ARMA model. While we have already established that we can in principle also fit non-stationary models with the ARMA model, remember that we had this classification of when an autoregressive model is stationary and when not, it's usually advisable to apply ARMA models only to stationary time series. So what we can do here is we can just apply the techniques that we've seen in the previous lessons in order to first get the stationary time series and then apply an ARMA model. And there is a way of integrating this, making the time series stationary directly into the ARMA model, which is then called SARIMA model, where E stands for integrated. And here remember that the integration is kind of the reverse process of differencing. So if we have an integrated model, in our formulas we want to apply differencing. And this is just what's been done in the SARIMA model. So the SARIMA model has now a new parameter d. Here the first parameter p gives the number of autoregressive lags, the number q gives the number of moving average lags, and d is the number of times we want to apply differencing to our time series. In the equation that looks just like that. As explained, before we want to apply the ARMA model, we want to make the time series stationary, and this is exactly what happens here. Now, first, we get rid of all the trends, and then we apply the ARMA model. So the SARIMA model on its own is already a very versatile model for time series forecasting. However, it lacks the possibility to model seasonalities, and that's the final step to develop the SARIMA model. So we've already learned about the AR as the autoregressive part, the I as the integrated part, and the MA as the moving average part. For the seasonal part, we are going to replay these three components with seasonal lags. That means that for the seasonal SARIMA, we do not only have the small p parameter for the autoregressive part, the small d for the integration part, and the small q for the moving average part, but we also have a large P for a seasonal autoregressive part, the large D for seasonal differencing, and the large Q for seasonal moving average. Additionally, we have this parameter M, which gives the period of the seasonality. So given that, we can directly write down the SARIMA model, which you see on the right here. So now the equation starts to look a little bit clustered, But no worries, let's look at the component and everything should become rather clear. So first of all, this part here removes all the seasonalities by doing leg M differencing. This part here removes all the trends by doing these order differencing. And this part here describes the seasonal autoregressive part. This part here describes the usual autoregressive part. And very similarly on the other side, we have here the seasonal moving average part and then the normal moving average part. So you see that in the end, the computation still is rather intuitive. So what is left to do in the last lesson is to apply this in the context of anomaly detection. We closed this module with a practical example. More precisely, we are going to fit the SARIMA model on the New York City taxi passengers dataset. So this dataset contains the number of taxi passengers in New York City in a time interval of 30 minutes. Good thing about this dataset is that there are some known anomalies in that. Namely, we have the New York City Marathon, Thanksgiving, Christmas, New Year's Eve, and a snow blizzard in January. We prepared a notebook for you that guides you through the individual steps of fitting a SARIMA model, containing also some practical advices of how to choose the parameters in the best way. There's no need to program anything. Of course, you are anyway invited to extend the mini-SAML solution that we've prepared for you. Please go through the cells and we'll meet each other again with the solution. All right, then let's see what we had there. So first of all, let's have a quick look at the data. In the upper row, you see the entire data set. Of course, this is kind of hard to recognize what's going on. So let's have a look at just 1 week of the data, which is what you see below. I think by now you clearly identify the seasonal pattern in the data, which has a weekly seasonality in this case. So now let's think a little bit about how to prepare the data. Remember that we had given our anomalies on a daily level while the original data was in 30 minutes intervals. There are definitely multiple ways to work with that. In this case, we've decided to aggregate the data on a daily level by taking the mean values for each day. So now let's talk about the parameterization of the SARIMA parameters. So first of all, we have seen no obvious trend in the data, meaning that we probably won't need to difference the time series. However, we've seen a seasonal pattern. So now let's try to determine good values for small p, small q, large P, large Q, and the period of the seasonality. Here are some rules of thumb how you can go about this. So first of all, let's talk about the Q, so the moving average part of our SARIMA model. Here we can refer again to the autocorrelation plot, and a typical value to choose would be the time step where the plot first meets the significant threshold. For P, so the autoregressive part, we can take the so-called partial autocorrelation function. We haven't talked about this so far, but we will see this in a minute. Here again, we have to look at when the plot meets the significant threshold. For M, the period of the seasonality, we can do what we've done before. We can take a look at the autocorrelation plot and then select the value with the highest autocorrelation. Now let's talk about the other seasonal components. For this large P, so the seasonal autoregression, we take a value larger than 1 if the ACM at M is positive. Otherwise, we take the value of 0. For Q, the seasonal moving average part, we take a value larger than 1 if the ACM at M is negative. And finally, for the seasonal differencing, we choose the value of 1 if the seasonal pattern is stable over time, and otherwise we take D equal to 0. So in general, it's also important to not choose too large values for P and Q. And a good rule of thumb here is usually that we want to have the sum of the large and the small d to be smaller or equal to 1. And similarly, the sum of the large P and the large Q to be smaller than 1. Please keep in mind that especially the seasonal differencing is rather expensive in terms of data, because when we lag with a lag of m, we basically lose m data points. So if we have a year-long seasonality, we basically use an entire year of our data. So that's the reason why we want to keep these values rather low. Here note, we haven't talked about the differencing part in the SARIMA model. This was because we did not observe any trend in our data. Otherwise, of course, we could use the methods that we've seen before in order to remove the trend and choose the D accordingly. So let's take these advices and apply them. So taking a close look at this autocorrelation function. So first of all, we can kind of ignore the first high correlations. These are most likely due to some autoregressive effects. But here, the next highest one that we can find is this at a lag of 7 days, which is also quite natural. Looking at the next highest point, we find this at a lag of 7 days, which also intuitively makes sense. There's one more value that we can read off the autocorrelation function, which is the value Q for the moving average part of the ARMA model. For this, it's best to first remove all the seasonal components, which is what we did, and then replotted the resulting autocorrelation function down below. In this plot, we can take a look for the first time that the value meets the significant threshold, which is at lag 3 here. So meaning that we can choose Q to be 3. So that's what we can read off the autocorrelation function. So for all the other values, we need to take a look at the partial autocorrelation function. So the partial autocorrelation function is slightly more complicated than the autocorrelation function. It basically measures the correlation between two variables if all the variables in between are observed. So this is the conditional covariance of xt and xt plus k, given that I observe all the values xt plus 1 till xt plus k minus 1. Then, of course, I normalize this with the conditional variance of these two variables. The partial autocorrelation is very well suited to determine the number of lags that we need for the autoregressive part, because a purely autoregressive process of order k would have partial autocorrelation of 0 for all the lags larger than k. So looking at the first time where we meet the significance threshold will give us a rather good idea of how to set this p. Now let's have a look at the partial autocorrelation function. And here we see that we meet the significant threshold at a lag of 1. So meaning that we just need one autocorrelation. So that means that we only need one autocorrelation lag. And with that, we have determined all the values that we need in order to specify our SARIMA model. So we are going to use SARIMA 103, 110 with a period of 7. So once we fitted the model, the stats model implementation of SARIMA already gives us a summary of how well the fit worked. So here you can see several measures of the quality of fit, like the log likelihood, the AIC, the BIC, and many more statistics about the quality of the fit. So we won't discuss all these values in detail, but we encourage you to look them up in case that you haven't heard of them so far. They all give valuable information about the quality of the fit. So, having a model, we can now use the forecasting error in order to identify anomalies. That means that we are going to predict the values of our time series in a one-step ahead prediction, meaning we take the necessary history into account and then re-predict all the values of our time series step by step, and then compare our forecasting output with the true value. A good thing about the SARIMA model is that it's fully probabilistic, meaning that we can easily compute confidence intervals around our prediction. And this is what you see below. Again, you can generate these plots automatically with stats models. There's nothing that you need to implement on your own. So what you see is the blue line is the true number of passengers per day. The green line is the forecast. And the light green area around it is the confidence interval. In this case, we have chosen to detect an anomaly whenever the true value lies outside of the confidence interval. I think you can already visually see that at least some of these points are indeed some of the anomalies that we've discussed earlier. Let's have a closer look at what we found and what we knew about this data set. Okay, here we see on the left side the anomalies that we knew in advance. And on the right side, we see the anomalies that we identified via forecasting. I invite you to pause the video for a moment, compare these two lists, and do you spot anything notable? Can you explain why we found more anomalies than we knew before? If you compared these two lists, you probably saw that we missed one of the anomalies that we knew about, which is the New York City Marathon, which was on the 2nd of November 2014. So this one we didn't got. But we identified a few more points. Namely, we also have the 28th of January. So here we can already conjecture that this might have something to do with the two anomalous days before, where we had the snow blizzard. So maybe still the taxi calls haven't fully recovered at this point. We can take a closer look at that. So we recognize two more points as anomalous, which we didn't have at our list, which is the 4th of December and the 2nd of January. So maybe it makes sense to have a look at the plot again and try to explain what we saw here. So first of all, you can see that we missed the New York City Marathon, but only just very slightly. So here the number was actually higher than we expected, but it was just still contained in the confidence interval. So basically here our threshold was just not high enough to recognize it. Even more interesting are the false positives that we got. For instance, we can look at the 4th of December. Here we can see that really the true time series does not look anomalous at all. However, our prediction expected a much lower value in this case. And maybe you also see the reason for that. Remember that we used a lag of 7 days to model the seasonal component of our SARIMA model, which is exactly the 27th of November, which was Thanksgiving. At Thanksgiving, we had a significantly lower number of taxi passengers when compared to other days. And this was used by our model in order to predict the 4th of December. So here we can see that the previous anomaly confused our model, which led to this false positive. So this is something that is very inherent to the SARIMA model. We can no longer expect that our SARIMA model really gives reliable forecast at this point. So if we would have done that in real life, we would have observed that Thanksgiving is really an anomaly. So maybe at this point we could have thought about, do we really want to use this value in order to predict into the future? Sometimes it can be a better choice to just impute the mean values here if we have reasons to believe that this will not affect the upcoming days. So we can find a similar reason for the other false positive that we had. That was just the 2nd of January. Again, this happened in the vicinity of other anomalies which are most likely responsible for these false positives in our case. So as a final comment, if we look at this time series, we can definitely spot another interesting point in time that did not appear in our list of known anomalies and is also not recognized by our model, which is exactly here when in the beginning of September. So what we see here looks really like a classical change point. So here we see that from a declining trend, we basically went up to a higher mean and without any apparent trend. So you can see again, this value just evaded detection by just staying just about in the confidence interval. Again, taking a lower threshold, we would have also detected this one. So again, I don't know really what it is. Since it is a change point, I think this is some seasonal effect that we see. Typically, maybe in autumn, we have more taxi calls on average. But this is just a conjecture of mine. All right, this concludes our model on time series analysis. In the next module, my colleague Misha Pachenko will talk about extreme value theory and how to apply it in anomaly detection.